Imagine looking up at the night sky and seeing not one, not two, but 5 suns blazing together in a cosmic dance. Sounds like something straight out of science fiction, right? Yet, these bewildering celestial arrangements, quintuple star systems, are very real, and they hide some of the most mind-bending secrets the universe has to offer. Most of us are familiar with binary stars, 2 stars orbiting each other, but systems with 5 stars locked in an intricate gravitational ballet. That's where the cosmos truly starts to show off. These rare and chaotic stellar families defy everything we thought we knew about how stars behave, and the discoveries astronomers have made about them are nothing short of extraordinary. What makes quintuple star systems so fascinating isn't just their rarity, though spotting one is like finding a needle in a galactic haystack. It's the sheer unpredictability of their dynamics. Picture 5 massive stars, each with its own gravitational pull, swirling around one another in patterns so complex they challenge our best supercomputers. The forces at play here create environments where time and space seem to warp, where orbits twist into impossible shapes, and where the laws of physics are pushed to their limits. And the strangest part, some of these systems shouldn't even exist according to our current models of star formation. Yet there they are, shining defiantly in the void, daring us to figure them out. This isn't just about stargazing, it's about unraveling one of the universe's greatest puzzles. Every new discovery in these 5 star systems throws another curveball at astronomers, forcing us to rethink how stars are born, how they live, and how they die. From planets that orbit multiple suns at once to bizarre gravitational interactions that seem to break the rules, the more we learn, the more questions we have. So, if you've ever wondered just how wild the cosmos can get, buckle up. We're about to dive into 30 of the most astonishing, head-scratching, and downright mysterious discoveries scientists have made about quintuple star systems, and trust me, by the end, you'll never look at the night sky the same way again. The first confirmed quintuple star system, known as HD 155358, was uncovered in the constellation Hercules, a find so unexpected it sent shockwaves through the astronomical community. What made this discovery so groundbreaking wasn't just the number of stars involved, but the sheer improbability of their arrangement. Imagine a celestial Russian nesting doll, 2 tight binary pairs orbiting each other, with a 5th star circling the entire group like a cosmic referee. Spotting such a complex dance required piecing together decades of observational data, as conventional telescopes often mistook these overlapping orbits for single points of light. Scientists used radial velocity measurements tracking the subtle wobbles of stars tugged by their companions' gravity to untangle the truth, but even then the data seemed impossible. The system defied expectations with its stability, as most multi-star systems this crowded should tear themselves apart within millions of years. Yet HD 155358 has endured for billions, forcing astronomers to revisit their models of stellar formation. The real kicker, one of the binary pairs is so close that their outer atmospheres practically touch, creating a swirling bridge of superheated plasma between them. Detecting systems like this is like listening to a symphony played by 5 orchestras at once. Each star's motion adds another layer of complexity. Early attempts often missed the subtle harmonies buried in the noise, dismissing them as instrument errors or cosmic static. It took advances in spectroscopy and space-based observatories to finally distinguish the individual voices in the chaos. Even now, researchers debate how such a system could have formed. Did it arise from a single collapsing gas cloud, or was it built over time through gravitational capture? Every answer leads to new questions, proving that the universe loves a good puzzle. One of the most baffling quintuple star systems ever observed is New Scorpii, where the heavens seem to have crafted a perfect celestial balancing act. Here, 2 tightly knit binary pairs whirl around each other in a delicate gravitational embrace, while a fifth star traces a wide, looping path around the entire ensemble. It's as if the universe staged a cosmic double date, with one lone observer circling at a respectful distance. The orbital choreography here is so precise that early astronomers dismissed it as a glitch after all. How could four stars in close proximity avoid catastrophic collisions or chaotic ejections? Yet New Scorpii has existed in this improbable arrangement for millions of years, quietly defying every assumption about multi-star stability. The secret lies in the staggering distances between these stellar partners. The binary pairs orbit each other at about the same span as Earth's distance from the Sun, close enough to interact, but not so close that their gravity tears them apart. Meanwhile, the fifth star maintains a far wider orbit, acting like a distant conductor keeping time for the entire system. This layered hierarchy of orbits creates a gravitational buffer, preventing the chaos that should, by all rights, rip the system apart. Modern simulations reveal that even tiny adjustments to these distances would send the stars spiraling into disarray, yet somehow New Scorpii found the perfect equilibrium. What's even more startling is how these configurations force us to rethink star formation. Traditional models suggest that such complex systems should be mathematical impossibilities, like balancing 5 spinning tops on a single fingertip. Yet New Scorpii and others like it suggest that stellar nurseries might be far messier and more dynamic than we ever imagined. Perhaps turbulent gas clouds in these regions fragmented in just the right way, or maybe gravitational interactions with passing stars sculpted these systems over eons. Either way, their existence hints at hidden chapters in the story of how stars are born. And then there's the light show. In New Scorpii's inner binaries, stars so close they nearly touch fling streams of superheated plasma into space, creating dazzling stellar winds that collide like cosmic fireworks. Meanwhile, the fifth star's gentle pull tugs subtly on the others, creating rhythmic variations in their brightness, a telltale clue that helped astronomers decode the system's structure. It's a reminder that these aren't just abstract puzzles. They're dynamic, evolving spectacles where even the faintest flicker of starlight can reveal universe-shattering secrets. Now picture this: a world where the horizon isn't lit by one sun, but 5. That's the reality for any hypothetical inhabitants of a planet in the Quintuple star system KY 5736, where astronomers made an astonishing find: a planet stubbornly clinging to orbit amidst the gravitational chaos. This wasn't just a fluke, it was a cosmic defiance of everything we thought we knew about planetary formation. Most planets emerge from the calm, dusty disks around single stars, where gravity can gently clump material together. But here, in a system where 5 stars tug and jostle like dancers in a mosh pit, a planet somehow managed to assemble itself and survive. The discovery sent shockwaves through the scientific community because, frankly, it shouldn't be possible. Planets need stability to form a quiet nursery where dust particles can stick together without being ripped apart by competing gravitational forces. Yet this world, likely a gas giant several times the size of Jupiter, orbits one of the system's stars while the other 4 loom ominously close. How did it avoid being flung into the void or shattered by gravitational tides? The answer might lie in its wide, cautious orbit, staying just far enough from the stellar frenzy to maintain its balance. But even then, the planet's very existence suggests that planetary formation is far more resilient and opportunistic than we ever imagined. What's even wilder is what this means for the search for extraterrestrial life. If planets can form in such extreme environments, the cosmic real estate for habitable worlds just expanded dramatically. Imagine a planet nestled in the Goldilocks zone of one star, bathed in the gentle glow of 4 others. The skies would be a perpetual light show, with suns rising and setting in unpredictable patterns, casting ever-shifting shadows. But the challenges would be immense: extreme temperature swings, erratic stellar radiation, and gravitational stresses that could trigger apocalyptic quakes. Yet life as we know it thrives in the most unexpected places. If microbes can survive in boiling vents at the ocean's depths or frozen Antarctic lakes, why not on a world with 5 suns? The implications stretch even further. If quintuple systems can host planets, then binary, triple, and quadruple systems might be teeming with them too, each with its own bizarre conditions. Suddenly, the galaxy's potential for weird, wonderful worlds feels limitless, and as telescopes grow more powerful, we might soon find Earth-like planets in these chaotic systems, pushing the boundaries of where we dare to look for life beyond our solar system. For now, KY 5736 stands as a tantalizing clue that the universe loves to break its own rules, and that the most unlikely places might just be where the next great discovery awaits. Among the strangest quintuple star systems ever discovered is one where the stars seem to defy cosmic logic, not by their number but by their birthdays. In most stellar families, stars form together from the same collapsing cloud of gas, like siblings born from the same parent. But in system TYC 703791111, astronomers found a jaw-dropping anomaly, 5 stars locked in orbit, some older than others by hundreds of millions of years. It's as if a toddler, a teenager, and a senior citizen were all holding hands in the same dance circle, leaving scientists scrambling to explain how such an unlikely grouping could exist. This discovery shatters one of astronomy's long-held assumptions, that stars in multi-star systems form at roughly the same time. Current models suggest that stellar nurseries fragment into clumps that collapse simultaneously, creating stars of similar ages. But here, spectral analysis revealed stark differences in composition and luminosity, with some stars showing advanced evolutionary stages while others appeared fresh from their cosmic cradle. The oldest star in the system burned brightly as a subgiant, well into its stellar middle age, while its youngest companion still flickered with the restless energy of youth. Theories abound. Perhaps the system formed through a rare capture event, where a passing star cluster tore through the region and left a few stragglers behind. Or maybe gravitational interactions in a densely packed nebula allowed stars of different generations to become entangled over time. The implications ripple far beyond this one peculiar system. If stars of wildly different ages can bind together, it suggests that stellar nurseries are far more dynamic and chaotic than we ever imagined. Turbulent regions of space might act like cosmic mixers, blending stars from separate birth events into shared orbits. This could mean that our galaxy's multi-star systems are far more diverse than the tidy, same-age groupings we've long assumed. And if that's true, it forces us to rethink how planets form in these environments. Could a planet orbiting an older star be bombarded with radiation from a younger, hotter sibling? Might the gravitational tugs of stars at different life stages destabilize orbits over time? What's truly mind-bending is how these age gaps reveal hidden chapters of galactic history. The older stars in the system act like cosmic time capsules, preserving the chemical fingerprints of the early universe, while their younger counterparts showcase newer, heavier elements forged in later generations of supernova. Studying this system is like reading a layered history book, one where each star tells a different story. For astronomers, it's a goldmine of clues about how star-forming regions evolve, how gravity sculpts strange alliances, and perhaps most importantly, how much we still don't understand about the universe's most fundamental processes. Deep within the constellation Orion lies a cosmic crime scene, a quintuple star system where one star didn't just leave, it fled. Astronomers studying the system HD 37255 discovered something chilling, the ghostly trail of a fifth star catapulted into the void at unimaginable speeds. This wasn't a peaceful departure. The star was hurled outward with such force that it's now a runaway, streaking across the galaxy at over 100 kilometers per second, leaving its 4 siblings locked in an unstable embrace. The evidence, a telltale wobble in the remaining stars' orbits, like a spinning top that's just been slapped, proof of a violent encounter that reshaped the system forever. The physics behind this stellar escape reads like a thriller. In densely packed multi-star systems, gravitational interactions can turn deadly. Picture 4 stars orbiting in tight formation, their paths chaotic but balanced until one strays too close to the others. A single misstep can trigger a gravitational slingshot, where the interloper steals energy from its siblings and gets launched like a cannonball. Alternatively, a close encounter between 2 stars could eject a third like a billiard ball struck at just the right angle. But in HD 37255's case, the culprit might have been even more dramatic. A near-miss collision that sent one star careening while the others recoiled in opposite directions. What's astonishing isn't just the violence, it's the aftermath. The ejected star's path traces backward to the system like a cosmic breadcrumb, allowing astronomers to reconstruct the cataclysm. Meanwhile, the remaining 4 stars now orbit in a lopsided configuration, their movements jittery and uneven. Simulations show this isn't just random chaos, it's the predictable result of a sudden mass loss, as if a tablecloth were yanked from under a spinning dinner plate. Surprisingly, such ejections might be more common than we thought. Scattered across the galaxy are rogue stars hurtling through space, many of which could be refugees from similar multi-star breakups. But the real mystery is what these events reveal about stellar adolescence. Young star systems are like volatile friend groups, where gravitational shoving matches can eject the weakest member without warning. For every HD 37255 we've found, there may be dozens where the runaway star has already vanished into the dark. This forces astronomers to reconsider how often these chaotic dramas unfold and what they mean for planets caught in the crossfire. Imagine a world orbiting one of these stars when the ejection occurred. Its sky lit by 4 suns one moment, then plunged into darkness the next as its host star goes rogue. The universe, it seems, has a flair for the theatrical, yet these catastrophes also birth new possibilities. Runaway stars carry the chemical makeup of their birth systems into uncharted regions, seeding distant corners of the galaxy with heavy elements. Some might even drag planets along for the ride, creating nomadic worlds adrift between the stars. Meanwhile, the systems left behind evolve into tighter, more stable configurations, proof that sometimes chaos is just the universe's way of tidying up. For astronomers, HD 37255 isn't just a curiosity. It's a time capsule preserving the moment gravity turned from architect to wrecking ball, reminding us that even the cosmos has its share of family feuds. Nestled within the swirling colors of the Sharpless 235 Nebula lies a quintuple star system that's not just surviving, it's painting the cosmos with light. Here, 5 young, fiery stars are cocooned in a dense cloud of gas and dust, their radiation sculpting the nebula into eerie pillars and luminous tendrils. This isn't just a random arrangement. It's a dynamic workshop where stellar winds and ultraviolet energy collide, turning the surrounding nebula into a celestial canvas. The stars don't merely exist within this space, they dominate it, bending the nebula's structure to their will. What makes this system extraordinary is how the stars' gravitational dance interacts with their gaseous cradle. The 2 innermost stars orbit so closely that their stellar wind streams of charged particles blowing outward at millions of kilometers per hour crash into each other, generating shock waves that heat the surrounding gas to incandescent temperatures. These collisions produce X-rays detectable across interstellar distances, like cosmic fireworks flashing in the dark. Meanwhile, the outer trio of stars carves bubble-like cavities in the nebula, their radiation pushing the gas outward like invisible hands molding clay. The result, a vast, glowing sculpture that changes shape over centuries, a testament to the star's relentless energy. But the real spectacle happens when the system's youngest star, still shrouded in a swirling disk of leftover formation material, erupts with sporadic outbursts. Like a temperamental artist, it occasionally flings massive jets of material light years into space, which punch through the nebula's layers and ignite new pockets of star formation. Astronomers call these Herbig-Haro objects glowing streaks of ionized gas that resemble celestial brushstrokes. It's as if the star system isn't just inhabiting the nebula, it's actively rewriting it, turning raw material into new stellar masterpieces. The implications stretch far beyond this one dazzling display. Systems like this challenge our understanding of how stars influence their birth environments. Conventional wisdom suggested that nebulae disperse quickly once stars ignite, blown away by their fierce radiation. But here, the quintet's collective gravity traps enough gas to sustain the nebula for millions of years longer than expected, creating a self-renewing stellar nursery. This could explain why some regions of space seem to birth stars in bursts like cosmic factories where one generation's activity fuels the next. For astronomers, the system is a living laboratory. By studying how these 5 stars ionize the nebula's hydrogen, they've uncovered clues about the early universe when the first stars lit up similar primordial clouds. The flickering shadows cast by dust lanes even reveal the system's 3D structure, like a stellar ballet viewed through a cosmic veil. And every new observation peels back another layer. Pockets of organic molecules detected near the stars hint that such systems might be cradles for the building blocks of life, churned out in the chaos of creation. Yet the most humbling realization, this light show isn't for us. The nebula's brilliance fades into the void unseen, a private performance on a scale we can barely fathom. It's a reminder that the universe thrums with activity beyond our gaze, where stars don't just shine, they sculpt, they destroy, and they create, all in the same breath. And in systems like this, we catch a fleeting glimpse of that raw, untamed power. Somewhere in the vast expanse of the Milky Way, a quintuple star system performs what might be the universe's most dangerous waltz, 5 stars locked in orbits so tight, their outer atmospheres nearly brush against one another. This cosmic feat, known as System Mizar Zeta, defies logic at every turn, with stellar partners circling each other at distances that would make our solar system's planets blush. The innermost pair completes an orbit in less than 2 Earth days, closer than Mercury is to the Sun, while the outer stars whip around at breakneck speeds, their gravity weaving an intricate net that somehow prevents catastrophe. What's truly staggering isn't just the proximity, it's the precision. For such a system to avoid tearing itself apart, every star must move in perfect sync, their gravitational pulls balancing like weights on a finely tuned scale. Picture 5 dancers spinning on a platform barely large enough to hold them, each adjusting their movements in real time to avoid collisions. A single misstep, a star drifting too close, would trigger a chain reaction of gravitational mayhem, flinging stars into chaotic orbits or even ejecting them entirely. Yet Mizar Zeta has maintained this dance for millions of years, a testament to the universe's knack for equilibrium. The secret lies in a phenomenon called hierarchical stability. Here, the stars organize themselves into tiers of orbits, tightly knit pairs within pairs, all bound by a central anchor star. Each layer operates like a set of gears. The innermost duo spins rapidly, their combined gravity acting as a single unit to the next pair, and so on, creating a gravitational buffer that dampens chaos. It's a celestial version of nesting dolls, where each layer shields the others from instability. But the real marvel, light doesn't behave normally here. The stars are so close that their radiation belts tangle, creating arcs of plasma that stretch between them like electrified bridges. At certain points in their orbits, these stars eclipse one another from our viewpoint, causing dramatic, rapid-fire dips in brightness, a telltale flicker that first alerted astronomers to their extraordinary arrangement. The heat is unimaginable. Stellar winds collide with enough force to generate X-ray flares visible across interstellar space, painting the system in a harsh, flickering glow. Yet this fragile balance raises haunting questions. How did such a system form in the first place? Conventional models suggest stars born this close would either merge or disrupt one another's orbits during their fiery infancy. One theory proposes a violent past, a stellar nursery so densely packed that newborn stars were nudged into these precarious orbits by passing siblings. Another hints at gradual migration, where gravitational interactions with gas disks or rogue planets slowly herded the stars into this improbable configuration. For astronomers, Mizar Zeta is both a puzzle and a revelation. Its existence suggests that our understanding of multi-star dynamics is still incomplete, hinting at hidden mechanisms that allow such extreme systems to thrive. Worse yet, simulations struggle to replicate its stability. Every digital model either collapses into chaos or ejects stars within virtual millennia. Yet there it glows, defiant, a cosmic tightrope walker that shouldn't exist but does, reminding us that the universe has a flair for the improbable. And perhaps most unsettling of all, this system is a ticking clock. Eventually, stellar evolution will disrupt its delicate balance. As the most massive stars age and expand, their outer layers will spill onto their neighbors, triggering eruptions or mergers that rewrite the system's fate. For now, though, Mizar Zeta spins on a fleeting masterpiece of gravitational choreography, daring us to unravel its secrets before the music stops. At the heart of the Quintuple system, V1357 Orionis, lies a cosmic phantom, an object so dark it reveals itself only through the terrified motions of its stellar companions. 4 brilliant stars whirl in chaotic orbits, their paths warped by an unseen force, while the 5th star remains eerily absent from telescopic images. This invisible menace emits no light, betrays no glow, yet its gravitational grip is undeniable. Something massive and dark lurks among these suns, likely a black hole or neutron star hiding in plain sight. The clues began piling up when astronomers noticed irregularities in the system's motion. Stars don't just orbit empty space unless something invisible anchors them. Radial velocity measurements showed one star being yanked back and forth as if tugged by an unseen leash, while infrared scans revealed bursts of X-rays flaring sporadically from nothing. These flares, lasting mere hours, matched the telltale signature of a black hole's accretion disk, superheated gas spiraling into oblivion at nearly light speed. But the real smoking gun came from the stars' orbits. Their erratic dance couldn't be explained by 4 stars alone. A 5th object, at least 10 times the sun's mass but emitting 0 light, had to be warping the fabric of space around them. What makes this discovery revolutionary isn't just the hidden object itself, it's how it got there. Black holes and neutron stars are stellar corpses, the remnants of dead stars that collapsed after violent supernova. But for one to coexist with 4 living stars in a stable orbit challenges everything we know about stellar life cycles. Normally, a supernova's explosive force would kick any remnant clear out of its system. Yet here, this dark entity sits snugly among its siblings, suggesting the original quintet might have weathered the cataclysm together, a cosmic miracle of survival. The implications rewrite galactic history. If black holes can lurk undetected in multi-star systems, our galaxy might be teeming with them. Previous surveys could have missed dozens, even hundreds of these shadowy hitchhikers simply because they weren't actively devouring matter. Worse yet, their presence could destabilize otherwise peaceful systems. A black hole's gravity might nudge planets into deadly orbits or strip away protective atmospheres with its radiation, raising eerie questions about how many habitable worlds might secretly orbit a silent killer. Yet the most tantalizing possibility is what this means for gravitational wave astronomy. When black holes or neutron stars orbit companion stars, their dance can spiral inward over eons until they collide, sending ripples through spacetime itself. Systems like V1357 Orionis could be ticking time bombs, their unseen components destined to crash in spectacular, universe-shaking events. Every flicker of X-rays, every wobble in the visible star's paths, is a clue to the invisible drama unfolding, one that might someday light up detectors here on Earth with echoes of a catastrophe we never saw coming. For now, this system remains a cosmic detective story where the absence of light speaks louder than any star. It's a reminder that the universe hides its most fascinating secrets not in what shines, but in what lurks patient, dark, and waiting to be found. In the Quintuple star system KIC 8462852, astronomers stumbled upon a cosmic mystery that left them utterly baffled. Stars that don't just orbit, but lurch through space like drunken dancers, speeding up and slowing down at random. This isn't the graceful, predictable motion of most stellar systems. It's as if something invisible keeps tugging on the stars, yanking them forward one moment and slamming the brakes the next. The erratic behavior defies every conventional model of orbital mechanics, leaving scientists to wonder, what kind of hidden force could possibly turn a star's trajectory into a roller coaster ride? The clues lie in the star's light. As they move, their brightness flickers in ways that betray sudden velocity, changes tiny, irregular dips and spikes that reveal violent, unseen influences. At first, researchers suspected a hidden planet or a dense debris field might be perturbing the star's paths, but the math didn't add up. Even a Jupiter-sized object wouldn't wrench a star's motion so dramatically without leaving other traces like dust clouds or infrared warmth. Then came a wilder theory. Perhaps the system is haunted by dark matter substructures, invisible clumps of the universe's most elusive material, warping space-time like unseen speed bumps in a cosmic road. But the most chilling possibility, a stealthy black hole not massive enough to fully disrupt the system, but just hefty enough to tug the stars unpredictably as it drifts through their midst. Picture a phantom shark circling a school of fish, its presence betrayed only by the panicked darting of its prey. If true, this would mark the first time a black hole's gravitational bullying has been detected indirectly through the erratic motion of stars. The implications are staggering. Most black holes are found either by their X-ray flares as they devour matter or by the ripples they create in space-time when colliding. But this one, it's playing hide and seek, leaving only these stellar speed wobbles as its calling card. What's equally bizarre is how localized the effect seems. Only 2 of the system's 5 stars exhibit these wild speed changes, while the other 3 orbit smoothly, as if oblivious to the chaos. This selective disturbance suggests the hidden force isn't evenly distributed. It's something that interacts with specific stars based on their mass, composition, or position. One theory proposes that the affected stars might have unusually extended magnetic fields, making them susceptible to interactions with a passing neutron star's powerful magnetism. Alternatively, their orbits might briefly intersect a dense knot of dark energy, a hypothetical cosmic texture rarely observed but long theorized. For now, KIC 8462852 remains a celestial riddle, challenging astronomers to rethink how hidden forces shape stellar motion. It's a reminder that even in the vastness of space, the universe loves to throw curveballs, and sometimes the most profound discoveries come not from what we see, but from what we can't explain. Some of the universe's strangest quintuple star systems might owe their existence to cosmic pile-ups, violent collisions between entire star clusters that leave behind tangled stellar families. Imagine 2 massive, speeding stellar nurseries slamming into one another, their gravity twisting and knotting like celestial spaghetti. In the chaos, stars don't just pass each other peacefully, they snatch one another into new orbits, forging bonds that last billions of years. That's the leading theory behind systems like HD 165351, where 5 stars of wildly different ages and compositions orbit in a configuration so peculiar, only a head-on collision could explain it. Evidence for this violent origin hides in the star's motions. Normally, stars in a system share similar velocities like cars cruising in the same lane. But here, some stars zip forward while others lag behind, as if they were once part of separate traffic flows suddenly merged. Spectroscopy reveals even more clues, varying levels of heavy elements, suggesting the stars formed in different nebulas before being thrown together. The smoking gun. Computer simulations show that when two young clusters collide at the right angle, their densest regions can plow through each other like interstellar freight trains, leaving behind a debris field of captured stars. Over time, gravity weaves the survivors into stable but bizarre configurations. The aftermath is pure cosmic improvisation. Stars that should never have met end up locked in intricate dances, their orbits skewed at odd angles. In HD 165351, one pair whirls perpendicular to the rest, like a gyroscope tipped on its side, a telltale sign of gravitational trauma. Meanwhile, the system's outermost star drifts suspiciously far, likely a straggler from the collision that hasn't fully committed to the group. These quirks are forensic evidence, helping astronomers reconstruct the crash's exact conditions, from the cluster's original sizes to their collision speed. But the real shocker is how common these events might be. Star clusters in our galaxy jostle like commuters in a crowded train station, especially in dense regions near the Milky Way's core. Statistically, thousands of quintuple systems could owe their existence to ancient pile-ups, stellar orphans adopted into chaotic new families. Some might even bear scars from the encounter, like distorted magnetic fields or unusually active stellar flares, as if the stars themselves remember the violence of their birth. What's truly humbling is the scale of time involved. These collisions unfold over millions of years, so slow to our eyes they might as well be frozen. Yet the systems they create endure for eons, carrying echoes of that primordial chaos in every wobble, every skewed orbit. For astronomers, they're more than just curiosities. They're time machines offering glimpses into the frenzied environments where the galaxy's most improbable stellar partnerships are born. And with every new quintuple system decoded, we're one step closer to understanding how the universe turns catastrophe into cosmic art. In the quintuple star system Ty Corvi, nature stages a spectacle unlike anything seen in our own cosmic neighborhood, a triple eclipse where three stars pass in front of one another in an intricate celestial lineup. From Earth's viewpoint, these stars align so precisely that one star briefly blocks the light of another, which in turn eclipses a third, creating a layered shadow play that defies imagination. The odds of such an event are staggeringly low, requiring not just multiple stars but orbits tilted at the perfect angle to our line of sight. It's like threading three needles simultaneously while they're all hurtling through space at thousands of kilometers per hour. What makes this phenomenon so extraordinary isn't just its rarity, it's the precision it reveals about stellar mechanics. For three stars to eclipse in sequence, their orbital planes must be nearly perfectly aligned with Earth, a configuration so precise that even slight deviations would make the event invisible to us. The inner binary pair of Ty Corvi orbits so tightly that they eclipse each other every few days, while the third star, slightly farther out, sweeps into alignment at just the right moment to complete the trio. When it happens, the system's combined light dims in a distinct stair-step pattern, a signature so unique it was initially mistaken for instrument error. Astronomers liken studying these eclipses to dissecting a cosmic clock. Each dip in brightness reveals critical details about the star's sizes, temperatures, and even their atmospheres. As one star passes in front of another, its silhouette leaves a fingerprint in the light spectrum, exposing elements in the eclipsed star's outer layers. But when three stars participate, the data becomes exponentially richer. The middle star's gravity subtly bends the light from the farthest one, an effect called microlensing, which can expose otherwise invisible features like stellar spots or swirling magnetic fields. The implications stretch beyond this one system. If triple eclipses can occur here, they might happen in other quintuple systems too. We've just never been lucky enough to catch them. Their existence suggests that multi-star systems can settle into astonishingly flat orbital arrangements over time, contrary to assumptions that complex systems should be inherently unstable. Some theorists propose that gravitational interactions with unseen planets or distant companion stars could act as cosmic sculptors, nudging orbits into these razor-thin alignments. Others wonder if the phenomenon is a fleeting phase, a momentary quirk of geometry that will vanish as the star's paths slowly drift apart. For stargazers, 2I Corvi offers a humbling lesson in perspective. From another angle in the galaxy, this system might look utterly ordinary, no eclipses, no dramatic light shows, but from our vantage point, it's a front-row seat to one of the universe's most meticulous performances. And with every observed eclipse, we're reminded that the cosmos doesn't just operate in broad strokes. It crafts its grandest marvels in the tiniest details, hidden in plain sight for those who know where and when to look. In the quintuple star system HD 167903, astronomers witnessed something that defies all expectation: stars that don't just burn steadily but erupt in unpredictable temperature swings, soaring from scorching hot to surprisingly cool in a matter of days. Imagine a campfire that suddenly turns into a blast furnace, then chills to embers, all without warning. These aren't ordinary stellar flares or gradual cooling cycles. They're violent, erratic shifts with no clear trigger, leaving scientists scrambling for answers. The first clue came from irregular dips and spikes in the system's light curve, betraying wild fluctuations in surface temperature. One star might blaze at 20,000 degrees, then plummet to half that heat within a week, behavior unheard of in stable stars. At first, researchers suspected colossal magnetic storms akin to our sun's solar flares but magnified 1,000-fold. Yet the temperature swings didn't match typical magnetic activity patterns. Instead of the gradual ebb and flow of a star's natural cycles, these changes were abrupt, almost chaotic, like a dial being cranked at random by an unseen hand. Then came a more unsettling theory: hidden interactions with an unseen companion. In multi-star systems, gravitational tugs can create tidal forces strong enough to distort a star's shape, stirring its interior and altering its heat output. But for these effects to cause such dramatic swings, the companion would need to be either incredibly dense, like a neutron star, or moving in an orbit so tight it brushes against the star's outer layers. Some astronomers speculate the culprit could be a dark stellar remnant, invisible to telescopes but palpable through its gravitational bullying. Picture a phantom star, long dead, still haunting its living siblings by rippling their surfaces with every close pass. Another possibility: the stars themselves might be locked in a feedback loop of instability. In tightly packed quintuple systems, one star's outburst could trigger a chain reaction, a stellar scream echoing through the group. Radiation from a flare might heat a neighboring star's atmosphere, ionizing gases and temporarily boosting its brightness, only for that star's subsequent cooling to destabilize the next. It's a cosmic domino effect where no single star acts alone, and the system's collective chaos becomes greater than the sum of its parts. Yet the most tantalizing clue lies in the star's composition. Spectral analysis revealed unusual abundances of heavy elements like iron and nickel, materials often forged in supernova. Could these stars have once had a sixth sibling that exploded, showering them with debris and leaving behind a hidden neutron star or black hole? The radioactive fallout might still be sinking into their cores, occasionally igniting violent convection currents that dredge up heat from the depths. For now, HD 167903 remains a puzzle wrapped in an enigma, challenging our understanding of stellar behavior. Every new observation peels back another layer, revealing just how little we truly grasp about the forces that govern these cosmic giants. And as long as these stars keep flickering like faulty light bulbs, they'll serve as a humbling reminder. the universe thrives on surprises, and even the most familiar objects can harbor secrets that defy explanation. Among the countless quintuple star systems scattered across the galaxy, one stands out not for its stars but for what swirls around them. In the system HD 983759, astronomers discovered a sprawling disk of dust and debris so vast it could span from the Sun to Neptune 100 times over. This isn't just space junk, it's a dynamic, churning nursery where gravity tirelessly works to sculpt new worlds, or the shattered remains of worlds that once were. The disk's sheer scale defies belief, glowing faintly in infrared as it absorbs starlight and re-radiates heat, a telltale sign of countless microscopic particles locked in an endless cosmic waltz. What makes this discovery so extraordinary is the battle raging within the disk itself. In most young star systems, dust particles gently clump together over millions of years, eventually forming planets. But here, 5 stars tug at the disk from different angles, their competing gravitational pulls stirring the material like a spoon in thick soup. Some regions are stretched into thin, spiraling streams, while others collapse into dense, chaotic knots. Computer simulations reveal that these conditions could either accelerate planet formation, pushing particles together faster than normal, or tear fledgling worlds apart before they ever take shape. It's a celestial tug of war where every clump of dust is a potential planet caught in the crossfire, yet the disk might not be a cradle at all, but a graveyard. Spectroscopic analysis detected unusual concentrations of silicon and carbon, materials often found in the shattered crusts of rocky planets. This raises a haunting possibility. The disk could be the mangled wreckage of a once stable planetary system, torn to shreds when the star's orbits shifted. Imagine a family of Earth-like worlds orbiting peacefully, only for a stellar sibling's gravity to suddenly go rogue, hurling them into collision courses that reduce them to swirling ash. The violence needed to create such a disk would be staggering, equivalent to pulverizing every planet in our solar system and scattering their remains across a volume 1,000 times larger. The system's youth deepens the mystery. At just a few million years old, a cosmic toddler compared to our 4.5 billion-year-old Sun, HD 983759, shouldn't have had time to form and then destroy planets. Unless, of course, multi-star systems forge and obliterate worlds at breakneck speeds. This would mean planets in such environments live fast and die young, their fate sealed by the unstable dance of their stellar host. For astronomers, the disk is a goldmine of clues. Its inner edge, sharply defined, hints at an unseen planet shepherding the debris, a snowplow in the chaos, using its gravity to carve a clean boundary. Meanwhile, telltale gaps in the disk structure suggest where other fledgling worlds might be coalescing, hidden beneath the dust, but the most tantalizing detail. The disk's outer regions contain complex organic molecules, the building blocks of life. If planets do form here, they'll be born into a soup of prebiotic material, raising the electrifying question of whether life could arise in such a turbulent cradle. Yet the very forces that make this system so fascinating also doom it to transience. Within a few million years, radiation from the 5 stars will blow much of the dust away, dispersing it into interstellar space. What remains will either solidify into new worlds or spiral into the stars themselves, consumed in flashes of fiery accretion. For now, though, HD 983759 offers a rare glimpse into the universe's creative and destructive fervor, where the line between birth and obliteration is as thin as a dust grain in the void. In the constellation Cygnus, astronomers tracking the quintuple star system KIC 7025183 stumbled upon a cosmic anomaly, stars that move as if guided by invisible hands, their orbits twisting in ways that defy every known gravitational equation. Predictions based on classical physics suggested these 5 stars should follow smooth, elliptical paths. Instead, their trajectories zigzag unpredictably, accelerating and decelerating without apparent cause. It's as if the laws of gravity here were rewritten by some unseen architect, leaving scientists to wonder, are we missing a fundamental piece of the universe's rulebook, or is something far stranger lurking in the darkness between these stars? The discrepancies first emerged when researchers tried to model the system's long-term stability. Even accounting for the stars' mutual gravitational pulls, their orbits should have destabilized within a few million years. Yet KIC 7025183 has persisted for over a billion, its stars weaving through space like a meticulously choreographed yet utterly inexplicable ballet. The most baffling behavior occurs in the outermost star, which occasionally stutters in its orbit as if caught in an invisible net. Traditional explanations faltered. No hidden planets or debris clouds could account for the sheer scale of these disturbances. One radical hypothesis suggests the system might be influenced by a primordial black hole, a relic from the universe's earliest moments, drifting unseen through the galaxy. These ancient objects, thought to weigh less than a mountain yet pack the mass of a star, could warp spacetime subtly enough to nudge stars off course without revealing themselves. Another possibility cuts even deeper into the unknown. Certain deviations align eerily with predictions of modified gravity theories, alternative frameworks proposing that gravity behaves differently under extreme conditions. If true, this system could be a laboratory for physics beyond Einstein's relativity, where the fabric of spacetime itself reacts unpredictably to the combined pull of multiple massive objects. Skeptics argue that instrumental errors or overlooked stellar phenomena could mimic these effects, but the data grows harder to dismiss with each new observation. The system's innermost stars add another layer of mystery. Their orbits precess, that is, slowly rotate at rates that shouldn't be possible without external influence. Normally, such precession hints at a nearby massive object, yet scans show nothing but empty space. Some theorists speculate that dark matter, if clustered in dense, invisible knots around the system, could exert the extra gravitational tug needed to explain the anomaly. Others propose a more exotic culprit: topological defects in spacetime itself, cosmic wrinkles left over from the Big Bang that subtly distort the paths of nearby stars. What makes KIC 7025183 so electrifying isn't just the unsolved puzzle, it's the stakes. If hidden matter or new physics bends the rules here, the same forces could be warping countless other systems, invisible to us only because we haven't looked closely enough. Every anomalous wobble, every defied prediction, is a clue that the universe still holds cards it hasn't shown us. And until we crack this celestial cipher, one thing remains certain: the cosmos is far stranger, far more mischievous than our textbooks dare to admit. Globular clusters are the universe's bustling mosh pits, tightly packed spheres of ancient stars where cosmic collisions and close encounters are the norm. So when astronomers stumbled upon a quintuple star system nestled deep inside one of these dense stellar swarms, it was like finding a perfectly intact house of cards in the middle of a hurricane. The system, catalogued as M13A7, defies expectations not just by existing in such chaos but by surviving it. Most multi-star systems in globular clusters get ripped apart by gravitational tugs from passing stars within a few million years. Yet here, 5 stars have clung together for billions, a cosmic miracle of endurance. The secret lies in their orbital dance. Unlike looser systems, where stars orbit at wide, vulnerable distances, these 5 are locked in a tight hierarchical embrace. The innermost trio forms a near-unbreakable gravitational knot, while the outer pair circles just far enough to avoid disruption but close enough to stay bound. It's a stellar survival strategy, like holding hands in a crowd to avoid getting swept away. Simulations suggest this configuration acts as a shield. When another star passes too close, the system flexes but doesn't shatter, redistributing the intruder's gravitational energy among its members like a cosmic shock absorber. But the cluster's crowded environment leaves its mark. The stars here are older and metal-poor, forged in the early universe when heavy elements were scarce. Their light carries the chemical fingerprints of a time before planets like Earth even existed. More striking are their bizarre orbits tilted and stretched by eons of gravitational harassment. One star in the system loops around at a steep angle, as if knocked askew by a long-ago collision. Another spins unnervingly fast, likely accelerated by a close encounter that robbed it of angular momentum. These scars tell a violent history, one where survival meant bending but not breaking. The real marvel, these stars shouldn't look like they do. In most of the universe, stars in tight binaries exchange mass, with one siphoning gas from the other until one becomes a bloated giant or a stripped-down husk. But M13 or 7 stars are all strangely similar, mid-sized, middle-aged, and burning steadily. The explanation might lie in the cluster's unique chemistry. With little dust or gas left to absorb energy, stellar winds here are weaker, reducing mass transfer between companions. It's as if the system evolved in a bubble, shielded from the extremes that warp stars elsewhere. Yet the greatest surprise is what this system reveals about globular clusters themselves. Once thought too chaotic to host complex stellar families, they might actually be cradles for some of the galaxy's most exotic configurations. If quintuple systems can form and endure here, hidden among hundreds of thousands of stars, how many others have we missed? The discovery forces astronomers to reconsider these ancient clusters not as destructive whirlpools but as cosmic petri dishes, where chaos and chance occasionally conspire to create something astonishing. And as telescopes probe deeper into these stellar beehives, who knows what other impossible partnerships might emerge from the noise? Deep within the quintuple system, HD 198346, the stars tell a story written in elements that shouldn't exist, at least not here. Spectroscopy reveals bizarre chemical fingerprints, stars laced with europium, gold, and even platinum, metals so heavy they typically sink into a star's core, invisible to telescopes. Yet these stars wear them like glittering cosmic jewelry, their surfaces shimmering with traces of materials forged in conditions far more violent than their current tranquil orbits suggest. It's as if someone sprinkled stardust from a supernova directly onto these suns, leaving astronomers to piece together how such exotic ingredients ended up in this celestial recipe. The leading theory points to a cataclysmic event in the system's past, a sixth star that met a spectacular end. When massive stars explode as supernova, they blast their innermost elements into space at nearly light speed. Normally, this material disperses too thinly to leave a mark, but in a tight-knit quintuple system, the ejected metals could have rained down onto the surviving stars, coating their outer layers like cosmic fallout. The timing had to be perfect. The supernova must have erupted just as the material was dense enough to enrich its siblings, but before their stellar winds could blow the debris away. Yet there's a twist. Some of these heavy elements aren't just sitting on the surface, they're mixed deep into the star's atmospheres, suggesting the contamination happened early, perhaps while these stars were still forming. This raises the electrifying possibility that the progenitor star didn't just die nearby. It might have been part of the original stellar nursery, exploding even as its siblings coalesced from the same gas cloud. Imagine a star's death throes seeding the birth of its replacements, its ashes becoming the building blocks for new suns. Alternative explanations are equally fascinating. The system could have plowed through an interstellar cloud laced with rare metals, scooping up material like a ship gathering ocean spray. Or perhaps one of the stars is secretly a vampire, siphoning enriched gas from a companion that's since been devoured, leaving only its chemical legacy behind. The most tantalizing clue: one star shows a bizarre overabundance of radioactive elements like uranium, which decay too quickly to linger from the system's birth. This hints at a far more recent injection, possibly from a neutron star merger somewhere in the neighborhood, whose gravity well-funneled precious metals straight into this cosmic waiting room. What makes this discovery revolutionary isn't just the odd chemistry, it's the window into how elements spread through the galaxy. These stars act like cosmic sponges, soaking up traces of events we'd never witnessed directly. Their atmospheres preserve records of ancient explosions, collisions, and wanderings, written in a language of spectral lines. For astronomers, it's like stumbling upon a library where every book recounts a different disaster, each adding another chapter to the story of how the universe builds and rebuilds itself. And the implications stretch beyond this one system. If quintuples can trap and concentrate rare elements so efficiently, they might be cosmic refineries where gold and platinum gather in quantities that could someday form metal-rich planets. Imagine a world where mountains gleam with primordial supernova debris, or where rivers carry dissolved stardust from an explosion that predated the sun. For now, HD 198346 remains a tantalizing clue that the universe's most precious elements might hide in plain sight, woven into the very fabric of stars that refuse to follow the rules. The quintuple star system Zeta Scorpii holds a cosmic horror story. One of its stars died long ago but refuses to fade away. Astronomers call it a zombie star, a stellar remnant that somehow survived the cataclysmic explosion of a supernova, defying every expectation of how massive stars meet their end. Normally, when stars go supernova, they either collapse into black holes or leave behind neutron stars' dense, dead cores that emit no visible light. But here, the fifth member of this system shines faintly yet persistently, its ghostly glow betraying the presence of something that by all rights shouldn't exist. What makes this survivor so unnerving is the violence it endured. Supernova unleash enough energy to obliterate anything within light years, yet this star remained gravitationally bound to its four siblings. Spectral analysis reveals its composition is bizarrely enriched with nickel and iron elements forged in the heart of the explosion, now swimming in its outer layers like shrapnel embedded in a wound. The leading theory suggests this might be a Thorn-Zitkow object, a hypothetical hybrid where a neutron star, the corpse of the exploded star, was ejected from its own core during the blast, only to later sink back into the outer layers of a partially destroyed companion. The result, a chimera, part living star, part dead stellar remnant locked in a macabre embrace. The implications rewrite stellar death certificates. If stars can partially survive supernova, then our models of these explosions are missing critical physics. Perhaps the blasts are lopsided, or maybe some stars shed enough mass beforehand to dampen the destruction. Worse yet, this isn't an isolated case. Other systems show similar chemical anomalies hinting at failed supernova, where stars convulsed but didn't fully detonate. Like cosmic horror villains, these undead stars force us to reconsider what it truly means for a star to die. For the remaining four stars in Zeta Scorpii, life with a zombie neighbor is fraught with peril. The remnant's gravity tugs erratically at the others, warping their orbits over millennia. Meanwhile, its radiation, a toxic mix of X-rays and gamma rays, bombards any potential planets, sterilizing them in a relentless barrage. Yet the system endures, a ghoulish testament to the universe's ability to defy expectations. Every flicker of the zombie star's light carries echoes of that ancient explosion, a reminder that even in the cold equations of astrophysics, there's always room for the inexplicable. Perhaps the most chilling realization: if stars can cheat death this way, the cosmos might be teeming with other stellar revenants hidden in plain sight, masquerading as ordinary suns until their dark secrets come to light. For astronomers, Zeta Scorpii isn't just a curiosity. It's a warning that the universe's rulebook has chapters we haven't even begun to read. Most star systems are cosmic free-for-alls, with orbits tilting every which way like a game of celestial pickup sticks. But in the quintuple system HD 188753, astronomers found something astonishing: 5 stars moving in near-perfect alignment, their orbits stacked flat like pancakes spinning on the same plate. This isn't just rare, it's downright eerie, defying the chaotic origins we expect from multi-star systems. Normally, stars forming together emerge from turbulent gas clouds that should scramble their orbits into random angles. Yet here, each star circles in the same pristine plane, almost as if some unseen force lined them up with cosmic precision. The secret might lie in how these stars were born. One theory suggests the system formed from an unusually calm, disk-shaped nebula, a stellar nursery so orderly that its rotation flattened all the forming stars into alignment, much like how planets in our solar system ended up orbiting the Sun along a single plane. Imagine a spinning pizza dough of gas and dust, with 5 lumps of stellar material condensing along its surface, all inheriting that same clockwise or counterclockwise spin. Over time, gravity would have locked them into this shared orientation, preserving their symmetry across billions of years. But there's a twist. Unlike single-star systems where planets form from leftover disk material, HD 188753 stars are too massive and far apart to have simply coalesced from a single disk. Instead, astronomers propose a 2-stage process. First, the original gas cloud fragmented into multiple dense knots, each collapsing into a star. Then, as these infant stars began orbiting, their collective gravity sculpted the remaining gas into a shared disk that forced their orbits into alignment, like marbles rolling into the grooves of a vinyl record. This disk-locking effect would have been strongest in the system's youth, when gas was abundant enough to exert drag on misaligned orbits. The system's architecture deepens the mystery. The inner trio of stars whirls in a tight clockwork dance, while the outer pair traces wider but equally flat orbits around them. This nested arrangement hints that the alignment wasn't just luck, it was baked into the system's structure from the beginning. Computer simulations show that for such perfect alignment to persist, the stars must have avoided disruptive encounters with passing clouds or rogue stars for their entire lives. Even a single close call could have yanked one star out of plane, like bumping a record player and sending the needle skidding. What's truly revolutionary is what this tells us about star formation. If disks can choreograph the orbits of 5 stars, they might be far more influential in shaping multi-star systems than we ever realized. Perhaps other seemingly chaotic systems started out just as orderly, only to be knocked askew by later disturbances. HD 188753, then, isn't just a curiosity, it's a time capsule preserving a primordial configuration that most systems lose, and the implications stretch beyond this one group of stars. If aligned quintuples exist, could there be sextuples or septuples with even more members sharing a plane? The discovery forces us to rethink how gravity and angular momentum conspire to create order in the cosmos, and whether, given the right conditions, the universe might prefer neatness over chaos after all. For now, this system stands as a cosmic oddity, a reminder that even in the vastness of space, perfection sometimes finds a way. At the heart of the quintuple system V1357 Orionis, astronomers found a star that breaks all the rules, a cosmic misfit whose very existence throws stellar evolution models into disarray. Dubbed the outlier, this star weighs in at nearly twice the mass predicted by its temperature and luminosity, like finding a hummingbird with the wingspan of an eagle. According to everything we know about star formation, such a mismatch shouldn't be possible. Stars of this mass should burn hotter and brighter, their nuclear furnaces raging in predictable ways. Yet here it sits, cool and dim for its size, quietly upending decades of astrophysical assumptions. The first clue came from spectral analysis. The star's light revealed an atmosphere rich in hydrogen but suspiciously devoid of heavier elements, a composition typically seen in ancient stars, not mid-sized ones like this. Even stranger, its magnetic field clocked in at 10 times the strength of similar stars, twisting space around it like an invisible fist. Some researchers initially dismissed the data as observational error, but repeated studies confirmed the impossible. This star had all the hallmarks of a stellar senior citizen, yet its position in the system suggested it was as young as its siblings. One radical explanation points to a stellar merger gone wrong. Perhaps two smaller stars collided long ago, their combined mass fusing into a single object that never quite settled into normal fusion. The resulting hybrid might have retained the chemical fingerprints of its ancestors while defying the usual mass-luminosity relationship. Supporting this, the star's outer layers show turbulent mixing patterns, telltale scars of a violent union. Yet simulations struggle to replicate such a merger without the star either exploding or spinning itself apart, leaving theorists grappling for alternatives. Another camp argues this could be the first observed dark matter star, a hypothetical object where invisible particles, not nuclear fusion, provide its energy. Certain dark matter models predict these exotic stars could form in dense environments, their cores acting as traps for weakly interacting particles. As these particles annihilate, they'd release energy that keeps the star shining without the usual heat or pressure. Intriguingly, V1357 Orionis orbits near the system's gravitational midpoint, where dark matter would naturally cluster. If proven, this would rewrite not just stellar physics but our understanding of the universe's invisible scaffolding. Skeptics counter that simpler explanations might suffice. Perhaps the star is enveloped in a disk of dust that dims its light, tricking us into underestimating its temperature. Or maybe powerful magnetic fields are suppressing convection in its core, distorting energy output. But each proposed fix raises new questions. Why doesn't the dust show up in infrared scans? How could magnetic forces remain so stable for millions of years? What makes this discovery so transformative isn't just the star itself, it's the implications. If one system can harbor such an anomaly, others might too, hiding in plain sight until our instruments catch the discrepancies. The outlier forces us to confront an uncomfortable truth. Stars, the very objects we thought we understood best, still have the power to surprise us. Whether it's a freak of nature or a signpost to new physics, this misfit star serves as a humbling reminder that the universe's textbook is still being written, and some of its most fascinating chapters might be hiding in the quiet defiance of a single, rule-breaking sun. In the depths of the cosmos lies a quintuple star system that plays a cruel trick on astronomers, a pair of stars so identical they could be cosmic mirror images. Catalogued as HD 162973, this system hosts twins matched with freakish precision, nearly the same mass, temperature, brightness, even rotation speed. The odds of such perfect stellar doppelgangers forming naturally are astronomically low, like finding two snowflakes with identical crystal patterns in a blizzard. Yet here they are, locked in orbit around three other stars, offering clues to one of the universe's most baffling stellar mysteries. What makes this pairing so extraordinary is the physics behind their creation. Stars typically form from collapsing gas clouds that fragment unevenly. Like tearing tissue paper, you never get two pieces exactly alike. Even binary stars, while often similar, show subtle differences in composition or age. But these twins defy expectations, their light spectra overlapping so perfectly that early observers mistook them for a single star. Only meticulous analysis of their orbital wobble revealed the truth. Two distinct stars separated by just a few million kilometers, each reflecting the other's properties with uncanny accuracy. The leading theory suggests an unusually serene birth environment, a nebula so uniform and stable that when it fragmented, two pockets collapsed under nearly identical conditions. Imagine two candles molded from the same wax, poured at the same temperature, and ignited by the same flame. Their matching spin rates hint that they formed from a single rotating gas clump that split cleanly down the middle like a cosmic cell dividing. Alternatively, they might have started as slightly mismatched siblings before gravitational interactions fine-tuned their properties. Over millions of years, tides between the stars could have synchronized their rotations while stellar winds stripped away any uneven outer layers, sanding them down into perfect matches. Yet the system's other stars add another layer of intrigue. While the twins orbit each other tightly, three larger, dissimilar stars circle them at greater distances. This hierarchical arrangement suggests the twins might be latecomers captured by the system after forming elsewhere, then sculpted into mirror images by their new environment. If true, it would mean the universe can manufacture stellar twins through nurture as well as nature, fine-tuning stars through gravitational encounters rather than birth conditions alone. The implications ripple through astronomy. If such precise duplication can occur naturally, it forces us to reconsider how often we might have mistaken twin stars for single objects in other systems. Their existence also provides a rare control group for stellar physics, a chance to study how small initial differences or the lack thereof shape a star's evolution. Most compellingly, they offer a glimpse into the delicate balance of star formation, where the slightest tweak in temperature, density, or spin can create wildly different outcomes, or against all odds, none at all. For now, HD 162973 stands as a cosmic hall of mirrors, reflecting not just light but the deepest questions about how stars emerge from chaos. And as astronomers scrutinize other quintuple systems for similar doppelgangers, one truth becomes clear: sometimes the universe's most profound lessons come in matching sets. In the chaotic ballet of the quintuple system HV 22116, stars don't just orbit, they brawl, stealing massive streams of gas from one another in a cosmic tug-of-war that reshapes their destinies. Here, gravity isn't just an invisible tether, it's a thief pulling material from one star and flinging it toward another in swirling, superheated rivers. The most dramatic heist involves the system's two closest stars, locked in such a tight embrace that their outer atmospheres constantly bleed into one another. One star, a bloated giant, acts as the donor, its loosely held gas siphoned away by its smaller but denser companion, which greedily collects the stolen material into a glowing accretion disk. Over millennia, this pirated fuel has transformed the thief into a blue straggler, a star that defies aging by replenishing its hydrogen supply, burning unnaturally bright and blue for its age like a cosmic vampire caught mid-feast. But the chaos doesn't stop there. The stolen gas doesn't always reach its intended target. In HV 22116, the other three stars stir the pot, their gravity warping the flow into unpredictable loops and eddies. Some material escapes entirely, forming shimmering bridges of ionized plasma that stretch across the system like tinsel caught in a storm. Other streams spiral inward, crashing onto the surfaces of unintended recipients in violent impacts that trigger sudden flares, stellar tantrums visible across light years. These collisions aren't gentle, they're catastrophic, releasing enough energy to vaporize planets 10 times over and leaving behind chemical scars. Spectrographs reveal bizarre isotopic ratios in the star's atmospheres, like oxygen-18, enriched to levels seen only in supernova debris, evidence of nuclear reactions sparked by the violent mixing of foreign material. What's truly bizarre is how these thefts alter stellar life cycles. Normally, stars evolve predictably, their fate sealed by their initial mass. But in this system, mass is fluid, traded like currency in a cutthroat marketplace. One star grows unnaturally massive, accelerating its death spiral into a supernova, while another, stripped of its outer layers, becomes a prematurely exposed core, its lifespan extended in a paradoxical twist. The system's third star shows signs of pollution, heavy elements like gold and uranium deposited onto its surface by rogue accretion streams, elements it could never have forged on its own. It's as if the stars are Frankenstein's monsters stitched together from stolen parts, their identities blurred by the constant exchange. the implications rewrite our understanding of stellar neighborhoods. If this kind of rampant theft is possible in quintuple systems, it might explain anomalies spotted elsewhere in the galaxy. Stars with mismatched compositions, rejuvenated stars glowing too brightly for their age, even odd supernovae that detonate prematurely. HV 22116 proves that stars aren't isolated islands, they're participants in a gravitational economy where mass is the ultimate commodity and theft is just another survival strategy. Yet the most haunting question remains: what happens to planets in such a system? Any world forming here would face apocalyptic conditions, solar winds shifting unpredictably as stars gain or lose mass, orbits destabilized by the system's ever-changing gravity, and skies lit by the flickering glow of stellar robberies in progress. It's a reminder that the universe's beauty often comes laced with violence, and that even the grandest cosmic dances can be, at heart, a fight for survival. Deep in the quintuple system HD 134762, something doesn't add up. The math insists there's an invisible dancer in this celestial waltz. For years, astronomers tracked the 5 visible stars, mapping their orbits with precision. But no matter how they crunched the numbers, the equations demanded a 6th presence. The stars wobbled erratically, their paths perturbed by an unseen force like marionettes tugged by a hidden string. The culprit, a stealthy stellar companion, too dim or distant to spot directly, yet massive enough to yank its siblings off course with every gravitational pirouette. Detecting this phantom star required cosmic detective work. Researchers turned to radial velocity measurements, tracking how the visible star's light subtly shifted as they were pulled toward and away from Earth by the unseen object's gravity. These shifts revealed a pattern. Every 83 years, the stars accelerated inexplicably, as if briefly yanked by an invisible hand. Then came the clincher. Infrared scans picked up a faint, warm glow in precisely the spot where calculations predicted the 6th star should lurk. Not bright enough to be a main sequence star, but too warm for a planet, the signal matched the profile of a cold brown dwarf or a dim red dwarf shrouded in dust. But the real breakthrough came from eclipses. One of the visible stars dimmed periodically, not just from its known companions, but from something else, a shadow passing silently between it and Earth. By timing these dips and reconstructing their geometry, astronomers triangulated the intruder's orbit, a wide, looping path that swung it close enough to disrupt the inner stars every few decades before retreating into the void. The 6th star, it seemed, was a recluse, lingering at the system's fringes like a cosmic hermit. The implications are profound. If a hidden star can hide undetected in a well-studied quintuple system, how many others might be lurking in plain sight? Current surveys could be missing entire populations of faint stellar companions, especially in chaotic multi-star environments where gravitational noise masks their presence. Worse yet, these phantoms might be sculpting systems in ways we've misunderstood, nudging planets into dangerous orbits or triggering stellar collisions with their quiet but relentless tugs. Yet the mystery deepens. This 6th star's orbit is oddly tilted compared to the others, suggesting it might not be a true sibling but a captured interloper, snatched by the system's gravity during a close encounter long ago. If true, it's a cosmic hitchhiker that's been along for the ride undetected, quietly rewriting the rules of its adoptive family. For astronomers, HD 134762 is more than a curiosity, it's a warning. Even in the most scrutinized corners of the sky, the universe still holds cards close to its chest, and sometimes what you can't see is the most fascinating part of the story. In the quintuple system KIC 41692111, astronomers discovered something that defies conventional stellar behavior: stars that pulse together like perfectly synchronized metronomes. Normally, variable stars brighten and dim according to their own internal rhythms, their fluctuations as unique as fingerprints. But here, 3 of the system's 5 stars oscillate in eerie harmony, their light curves rising and falling in lockstep despite being separated by millions of kilometers. At first glance, it seemed impossible, like 5 pendulums swinging at different lengths, yet somehow keeping perfect time. The synchronization is too precise to dismiss as coincidence. Every 47 hours, the trio's brightness spikes simultaneously, their surfaces heaving outward in unison before settling back into rhythm. This isn't just superficial similarity. Spectroscopic analyzers confirm their outer layers physically expand and contract in tandem, as if connected by invisible threads. The leading theory, gravitational resonance, a phenomenon where orbiting bodies influence each other's movements until their cycles align. In this case, the stars' mutual tugs may have gradually tuned their pulsations like musicians in an orchestra finding harmony through endless rehearsal. Yet the mechanics baffle even seasoned astrophysicists. For resonance to work across such vast distances, the system's gravitational conservation would need to be improbably efficient. One hypothesis suggests the stars transfer energy through subtle distortions in their shared magnetic fields, creating a feedback loop that coordinates their pulses. Another proposes that tidal forces, the same gravitational nudges that make Earth's oceans rise and fall, are stretching and compressing the stars' outer layers in perfect sync. Computer simulations show that under just the right conditions, these forces could act like a cosmic drumbeat, setting a rhythm the stars can't help but follow. What's truly bizarre is how selective the effect seems. The system's 2 remaining stars pulse erratically, oblivious to their siblings' coordination. This hints that orbital geometry plays a starring role. The synchronized trio might occupy a sweet spot where their distances and masses create ideal conditions for resonance, while the outliers orbit too close or too far to join the dance. It's a celestial version of selective hearing, where only certain stars pick up the rhythm. The implications ripple beyond this one system. If stars can synchronize their pulsations across such ranges, it could explain oddities in other variable star clusters, where apparent coincidences might actually be orchestrated by hidden gravitational symphonies. For astronomers, KIC 4169211 is more than a curiosity. It's a natural laboratory for studying how deeply interconnected stars can become. And then there's the lingering question, could this synchronization influence planets? In theory, the rhythmic stellar pulsations would create waves of radiation that sweep through the system like a lighthouse beam. Any orbiting worlds would endure regular, coordinated surges of heat and charged particles, conditions that could either sterilize their surfaces or, in rare cases, spark complex chemistry in their atmospheres. It's a reminder that even the strangest cosmic phenomena might have consequences we're only beginning to imagine. For now, this system stands as a testament to gravity's hidden harmonies, proving that even in the chaos of space, order can emerge not by design, but through the patient, inexorable pull of physics. And as telescopes grow sharper, who knows how many other stellar choruses we'll find, singing in unison across the dark. Among the rarest cosmic families is the Quintuple system, HD 132567, where all 5 stars share a chemical fingerprint so precise they might as well be quintuplets born from the same stellar womb. Spectroscopy reveals their atmospheres contain identical ratios of iron, oxygen, and even rare metals like europium, elements typically scattered unevenly across star-forming regions. This eerie similarity points to a singular origin, all 5 stars condensed from the same primordial gas cloud, inheriting its unique elemental recipe like siblings sharing DNA. What's truly baffling isn't their shared birth, but how drastically they've diverged since. One star burns as a blue-white inferno, its surface temperature triple that of the Sun, while another smolders as a cool red dwarf barely massive enough to sustain fusion. A third pulses erratically, its brightness swinging like a malfunctioning bulb, while its 2 companions spin so rapidly their shapes bulge at the equator. These disparities defy expectations. Stars born together should mature at comparable rates. The answer lies in a cosmic twist of fate, their initial masses. Even minute differences in their starting weights, as slight as 5%, cascade into wildly different fates over billions of years. The heaviest star devours its nuclear fuel recklessly, living fast and dying young, while the lightest conserves its hydrogen like a frugal hermit, stretching its lifespan for trillions of years. But mass isn't the only sculptor here. Their intricate dance plays a role too. The tightest binary pair exchanges mass through filamentary bridges of superheated gas, the donor star growing leaner while its partner bloats with stolen fuel. Meanwhile, the system's lone wolf, a star drifting slightly farther out, spins unnervingly slow, likely braked by magnetic interactions with the surrounding nebula's remnant dust. These environmental quirks amplify their differences, turning subtle initial variations into stark contrasts. It's as if identical twins were raised in different climates, with one becoming a sprinter and the other a sumo wrestler. The system's history is written in its outliers. One star shows elevated levels of lithium, an element usually destroyed early in a star's life. Its presence suggests this star avoided the deep mixing that churns lithium into fusion furnaces, possibly because it was born with an unusually strong magnetic field that inhibited internal circulation. Another star's spectrum reveals traces of carbon-13, an isotope typically found in planetary atmospheres. This hints at a cataclysmic past where it engulfed a carbon-rich world, absorbing the planet's remains into its outer layers. What makes HD 132567 so extraordinary isn't just its diversity, it's the reminder that stellar evolution is never predestined. Even stars forged from the same materials under the same conditions can rewrite their destinies through gravitational encounters, magnetic fields, or sheer cosmic luck. For astronomers, this system is a time-lapse portrait of how randomness and inevitability intertwine, proving that the universe never paints by numbers even when starting with the same palette. Hidden within the tangled orbits of the Quintuple system VV347, something sinister lurks, a star that refuses to age gracefully, sustaining its youth by feeding on its siblings. Astronomers call it a blue straggler, an anomaly that glows unnaturally bright and blue compared to its stellar kin, like a 40-year-old with the complexion of a teenager. This cosmic vampire doesn't rely on mythical powers. It operates through brutal gravitational theft, siphoning hydrogen-rich plasma from its closest companion through a superheated bridge of stolen material. With every passing millennium, the victim star grows dimmer, its outer layers peeled away while the vampire grows brighter, its core reignited with fresh fuel. The mechanics of this stellar cannibalism are both elegant and merciless. The two stars orbit so closely that the vampire's gravity overpowers its neighbor, distorting the donor star into a teardrop shape. Matter from the victim's outer atmosphere spills past the point of no return, the Roch lobe where the thief's gravity takes control, funneling gas into a swirling accretion disk before it spirals down onto the vampire's surface. This stolen hydrogen doesn't just sit idle, it reignites nuclear fusion in the predator's core, effectively hitting the reset button on its life cycle. The donor, meanwhile, faces a grim fate. Stripped down to its dense helium core, it may end its days as a smoldering white dwarf, its substance absorbed into its brighter, rejuvenated sibling. The system's other three stars play unexpected roles in this drama. Their gravitational influence prevents the binary pair from merging outright, stabilizing the theft at a sustainable rate. One star, drifting slightly farther out, acts like a cosmic referee. Its gentle tugs keep the vampire from draining its prey too quickly, extending the feast over hundreds of millions of years. Meanwhile, the outermost star shows signs of its own past trauma. Spectral lines reveal elevated levels of carbon and nitrogen, elements typically dredged up from a star's core during mass transfer. This hints that it might have once been a vampire itself, now retired after exhausting its original donor. What's truly unsettling is how this process rewrites stellar evolution. Normally, a star's lifespan is set at birth by its initial mass, but blue stragglers cheat this inevitability, using stolen fuel to shine longer and hotter than their natural expiration date should allow. In VV347, the vampire appears 2 billion years younger than its peers, a discrepancy that once baffled astronomers until they pieced together its predatory history. This discovery forced a paradigm shift. Stellar populations aren't always what they seem. What looks like a young star cluster might instead be an old one hiding a few well-fed vampires among its ranks. The consequences ripple beyond this one system. Planets orbiting the vampire face apocalyptic conditions, brutal ultraviolet radiation from the star's unnatural brightness, gravitational chaos from the ongoing mass transfer, and potential orbital instability as the system's balance shifts. Any life that somehow arose here would endure skies lit by the slow-motion disassembly of one sun by another. Yet for all its violence, this process seeds the cosmos with heavy elements. The stolen plasma, heated to millions of degrees in the accretion disk, forges trace metals that will someday be incorporated into new stars, planets, or even life forms. Astronomers now suspect such vampirism might be shockingly common in multi-star systems, where gravitational interactions create ideal conditions for stellar theft. Every blue straggler found is a clue pointing back to a hidden history of cosmic robbery, written in the light of stars that refuse to fade quietly. VV347 stands as a stark reminder. The universe harbors no saints, only survivors, and sometimes the brightest flames burn only because they've learned to feed on others. In the cosmic pinball machine of quintuple star systems, HD 186168 stands out as an orbital heretic, a system where one star defies the universal choreography by spinning backward. While most stars in multi-systems orbit in the same direction like synchronized swimmers, this rogue performer moves against the flow, tracing a retrograde path that flips stellar dynamics on its head. Imagine 5 dancers circling a stage, 4 twirling clockwise in perfect harmony while the 5th insists on waltzing counterclockwise, bumping elbows with the others at every turn. This isn't just an oddity, it's a cosmic crime scene, and the evidence points to a violent past that reshaped the system forever. The discovery shattered expectations because retrograde orbits in multi-star systems are vanishingly rare. Gravity prefers order. When stars form from a single rotating gas cloud, they inherit its spin direction like children learning to dance from the same instructor. For one star to reverse course requires an intervention brutal enough to overpower this natural momentum. Astronomers reconstructing the system's history landed on 2 plausible scenarios, each more dramatic than the last. The first involves a near-miss catastrophe. Billions of years ago, another star or massive planet might have barreled through the system, its gravitational slingshot yanking one star into a backward spiral. Picture a billiard ball striking a spinning top hard enough to reverse its rotation, an event so violent it permanently scarred the system's architecture. The second theory is even more extreme, a stellar hijacking. The rebel star might not be an original member at all, but a wanderer captured from a passing star cluster. If it came from a cloud rotating the opposite way, its retrograde motion would be a stubborn holdover from its birthplace. Supporting this, the star's composition shows subtle chemical differences from its siblings, like a foreign accent betraying its extragalactic origins. The capture would have been chaotic, with the intruder's gravity flinging other stars into new orbits before the system finally settled into an uneasy truce. What makes HD 186168 so mesmerizing isn't just the backward orbit, it's the ripple effects. The rebel star's path crosses the others at steep angles, creating gravitational shockwaves that propagate through the system. During close passes, tidal forces stretch the star's atmospheres, triggering bursts of stellar flares visible across interstellar distances. Meanwhile, the misalignment warps any potential planetary orbits into pretzel-like shapes. A planet here would experience seasons where the sun rises in the west or loops erratically across the sky. The system's existence challenges our models of cosmic harmony. If retrograde stars can persist for billions of years, other, impossible configurations might lurk undetected. Worse yet, these backward orbits could be more than curiosities. They might be time bombs. Simulations show the rebel star's path growing increasingly unstable, its orbit decaying until millions of years from now, it either collides with a sibling or gets ejected entirely. For astronomers, HD 186168 is a fleeting glimpse of cosmic rebellion, a reminder that even the strictest laws of physics leave room for the occasional renegade. And as telescopes uncover more of these outliers, we're forced to confront an unsettling truth. Sometimes the universe's greatest lessons come from the stars that refuse to follow the rules. In the Quintuple star system KIC 8463212, astronomers witnessed something that defies all conventional logic. Stars that flash unpredictably, erupting in bursts of light so intense they outshine their normal luminosity by a factor of 10. These aren't the steady pulses of variable stars or the rhythmic flickers of eclipsing binaries. These are violent, erratic flares, appearing without warning and vanishing just as suddenly, like cosmic Morse code written in bursts of raw energy. At first, scientists assumed they were observing extreme stellar flares, magnetic tantrums from turbulent suns, but the patterns didn't match. The flashes weren't tied to stellar rotation or sunspot cycles. They arrived randomly, sometimes separated by months, sometimes clustered in rapid succession, as if the stars themselves were flickering like faulty light bulbs. The mystery deepened when researchers analyzed the light spectra. Each flash carried an unusual signature, an excess of infrared radiation that lingered briefly before fading. This afterglow suggested something beyond mere stellar activity. One radical hypothesis proposed that the flashes might be artificial signatures of alien megastructures, like Dyson swarms or massive energy collectors, briefly obscuring the star's light as they rotated or adjusted their positions. The idea wasn't entirely far-fetched. Similar anomalies in other stars had sparked debates about extraterrestrial engineering before, yet the sheer scale of what would be required boggles the mind. To dim or brighten multiple stars in a coordinated manner would demand technology far beyond anything humanity could envision, a civilization capable of harnessing entire stellar systems as power sources. Skeptics countered with natural explanations. Perhaps the flashes stem from a yet undiscovered stellar phenomenon, magnetic reconnection events on a scale never before observed, where tangled field lines snap and release energy in colossal bursts. Alternatively, the system might host a dense debris disk laced with asteroid-sized chunks of highly reflective metal. When these fragments align just right, they could act like cosmic mirrors, focusing and amplifying starlight toward Earth in fleeting, dazzling flashes. Supporting this, the system's infrared excess could point to warm dust, the remnants of ancient collisions still hovering in unstable orbits. The truth might lie somewhere even stranger. Some theorists speculate the flashes could be echoes of a past catastrophe, light from a long-ago supernova or stellar collision bouncing off distant dust clouds and only now reaching us. Like a cosmic hall of mirrors, the light takes different paths, arriving at Earth in disjointed fragments that appear as random bursts. Others wonder if the quintuple system's complex gravity is warping spacetime itself, creating lensing effects that magnify background stars intermittently as the orbits shift. What makes KIC 8463212 so compelling isn't just the mystery, it's the implications. If the flashes are natural, they represent a new class of stellar behavior that could reshape our understanding of magnetic fields or interstellar debris. If they're artificial, they hint at technologies so advanced they border on magic. For now, the system remains an enigma, a cosmic riddle written in bursts of light. And as telescopes grow more sensitive, who knows what other secrets might flicker into view, beckoning us to look closer, to question deeper, and to wonder whether the universe's greatest puzzles are yet to be solved, or if we're only beginning to ask the right questions. Most star systems cling to their members like tight-knit families, but the quintuple arrangement of HD 157309 plays by different rules. Its stars are stretched so far apart, their gravitational bond borders on the unbelievable. Imagine 5 dancers spread across a vast stage, each moving independently yet somehow staying in sync despite being barely aware of the others. The outermost stars in this system drift over a light year apart, a distance so immense the gravitational pull between them is weaker than a spiderweb holding together freight trains. By all rights, such tenuous connections should have snapped long ago, scattering these stars into the galactic void. Yet against every prediction they persist, their delicate celestial waltz continuing uninterrupted for billions of years. The secret to their survival lies in an intricate orbital hierarchy that turns weakness into strength. While the inner trio of stars orbits relatively close, forming a stable gravitational anchor, the outer pair traces such wide, looping paths that their tugs on the system are more like gentle suggestions than commands. This layered structure creates a buffer like a rubber band stretched to its limit but never quite breaking. The inner star's tight bond absorbs most disturbances, shielding the fragile outer connections from passing nebulae or rogue stars that might otherwise sever the link. It's a cosmic balancing act where proximity and distance exist in perfect tension. Yet the system's fragility raises profound questions about how such configurations arise. Traditional models suggest quintuple systems form from dense, collapsing gas clouds where stars are born shoulder to shoulder. But HD 157309's sprawling architecture hints at a far messier origin. Perhaps a chance encounter between 2 smaller star clusters that became gravitationally entangled over millennia. Supporting this, spectroscopic analysis reveals subtle differences in the star's chemical compositions, as if they originated in separate stellar nurseries before being drafted into this unlikely alliance. What's truly baffling is how the system maintains cohesion without obvious external forces. Some theorists propose an invisible glue, dark matter permeating the system in dense filaments that add just enough gravitational scaffolding to prevent collapse. Others argue the stars might be coasting on borrowed time, their slow motion escape delayed by the galaxy's ambient gravitational field. Like leaves caught in a gentle eddy, they appear stationary even as the current gradually carries them apart. The implications challenge our understanding of stellar dynamics. If such barely there systems can endure, the galaxy might harbor countless other ultra-diffuse families hiding in plain sight, their stars so distant they've been misclassified as loners. Worse yet, their existence suggests gravitational bonds are more resilient than we thought, capable of persisting across scales that defy intuition. For astronomers, HD 157309 isn't just an outlier, it's a stress test for the laws of physics, proving that even the universe's faintest whispers can sometimes echo forever. One of the most unsettling cosmic mysteries lies in the quintuple system HD 139691, where astronomers witnessed the impossible, a star that simply blinked out of existence. One day it burned brightly in telescopic observations. The next, its light vanished without a supernova, without a trace, as if someone had flipped a switch in the void. The 4 remaining stars continued their dance undisturbed, leaving no debris, no shockwave, not even a ripple in the surrounding dust clouds. It was a cosmic magic trick with no explanation, defying every known law of stellar evolution. Theories erupted like supernova in the scientific community. Some argued the star must have collapsed directly into a black hole, a phenomenon called failed supernova, where a massive star's core implodes without the usual explosive fanfare. Normally, such collapses still emit neutrinos and gravitational waves, but none were detected. Others proposed an even wilder idea. The star might have been ensnared by a primordial black hole, an ancient relic from the Big Bang lurking unseen in the system. Like a spider consuming prey, the black hole could have swallowed the star whole, leaving only its gravitational shadow behind. Yet skeptics questioned whether the star existed at all. Early observations might have misidentified a transient reflection or a glitch in the data, a cosmic illusion amplified by wishful thinking. Telescopes have limitations. Sometimes light from distant quasars or passing asteroids masquerades as stars before vanishing. But the evidence tilted toward something darker. Archival infrared scans showed an anomalous heat signature exactly where the star should have been, as if its remnants were still radiating faintly, cloaked in dust. The most chilling possibility: the star didn't vanish, it was shrouded. Advanced civilizations, if they existed, could theoretically build Dyson spheres or other megastructures to harness a star's energy, blocking its light from external viewers. While fringe, the hypothesis underscores how little we understand about the extremes of cosmic behavior. For now, HD 139691 remains an open case file, a reminder that the universe's greatest enigmas aren't always about what's there, but what isn't. And somewhere in that silence, between the gaps of our knowledge, a star's absence speaks louder than any explosion ever could. Somewhere in the depths of the cosmos, the quintuple system V907 Scorpii writhes like a wounded beast, its stars locked in a gravitational death spiral that can only end in catastrophe. Astronomers call it the most unstable multi-star system ever discovered, a ticking time bomb where 5 suns teeter on the brink of annihilation. Here, gravity isn't just a force, it's an executioner, patiently unraveling the bonds between stars with each chaotic orbit. The innermost trio whips around one another at breakneck speeds, their paths crisscrossing so closely that tidal forces strip away their outer atmospheres, creating glowing halos of superheated plasma. Meanwhile, the outermost pair spirals outward in increasingly erratic loops, their connection to the group weakening with every rotation like fraying rope fibers about to snap. This isn't just random chaos, it's celestial mathematics playing out in real time. Simulations reveal the system's fate with chilling precision. Within the next 200,000 years, the outermost star will slingshot free, ejected into interstellar space at over 300 kilometers per second. The remaining 4 will collapse into a tighter configuration, only for another star to be hurled away moments later in a gravitational chain reaction. By the time the fireworks end, 3 stars may remain, or none at all, scattered across the galaxy like cosmic shrapnel from a stellar grenade. The process is already visible in their motions. Precise astrometric measurements show the outermost star accelerating unpredictably, its velocity fluctuating as if the system itself is gasping for equilibrium. What makes V907 Scorpii so valuable isn't its impending destruction, it's what that destruction reveals about stellar mechanics. Normally, multi-star systems evolve too slowly for humans to witness meaningful change. But here, the unraveling unfolds at a relative sprint, offering a front-row seat to processes usually glimpsed only in computer models. The system behaves like a laboratory for dynamical instability, demonstrating how gravitational interactions can amplify tiny orbital deviations into system-shattering chaos. One star's slight wobble triggers another's erratic leap, which disturbs a third, a phenomenon astronomers call resonance overlap, where competing gravitational rhythms push each other offbeat until the entire ensemble collapses. Yet the most startling lesson lies in the debris. As stars are ejected, they'll carry traces of their siblings' chemical makeup into the galactic void, a form of cosmic diaspora that might explain mysterious rogue stars found wandering between galaxies. Meanwhile, any planets in the system face apocalyptic conditions. tidal forces would stretch their orbits into grotesque ellipses, triggering volcanic cataclysms or hurling them into their host stars. Any life clinging to survival would witness skies torn apart, suns drifting away into darkness, while others grow terrifyingly large before vanishing in a final gravitational kick. For astronomers, V907 Scorpii is more than a doomed curiosity. It's a Rosetta Stone for decoding the violent lives of multi-star systems. Its death throws mirror processes believed to shape globular clusters and galactic cores, where stars jostle in similarly crowded environments. By studying its collapse, we might finally understand why some systems endure for billions of years while others tear themselves apart in cosmic infancy. And as telescopes monitor its final act, one truth becomes undeniable. Even the universe's most fleeting phenomena can illuminate its deepest laws if we're bold enough to watch. From 5 suns locked in impossible orbits to vanished stars and cosmic vampirism, quintuple star systems have rewritten the rules of stellar physics. They've shown us planets that form in gravitational chaos, stars that pulse in eerie synchrony, and black holes hiding in plain sight. We've witnessed systems where entire stars flee at breakneck speeds, where stellar siblings defy age gaps spanning hundreds of millions of years, and where the faintest gravitational whispers hold entire families together across light years. Each discovery peels back another layer of the universe's ingenuity, proving that even our wildest models can't outpace the creativity of cosmic reality. These systems aren't just celestial oddities, they're stress tests for our understanding of gravity, stellar evolution, and the very fabric of space-time. When a star vanishes without a trace or a zombie stellar remnant cheats death, it forces astronomers back to the drawing board. When 5 suns align flawlessly or a rogue star spins backward, it reveals gaps in our knowledge wider than the orbits themselves. Quintuple systems remind us that the universe thrives on exceptions, turning impossible into a challenge rather than a verdict. Now it's your turn. Which of these 30 discoveries left you breathless? Was it the planet stubbornly clinging to orbit amidst 5 gravitational bullies, or the stars that flicker like cosmic Morse code? Perhaps the vampire star feasting on its siblings, or the phantom black hole lurking undetected? Drop your favorite in the comments or shout out another cosmic mystery that keeps you staring at the night sky, wondering what else is out there rewriting the rules. Because if quintuple star systems have taught us anything, it's that the universe's greatest surprises are still waiting to be found.